Hello, geometry students. I appreciate you finding time to get your notes taken care of. Today we're going to be looking at a little bit more advanced type of a shape and seeing if we can't calculate its area. And today we are looking at the regular polygons. Please copy down the title as well as the objective. Our objective for this day is the student will learn the formula and process for finding areas of regular polygons. Now, regular polygons are obviously a pretty specialized shape, and remember the definition of regular is that they're going to be both equiangular and equilateral at the same time. As such, they're going to develop certain properties to go along with them, and those properties are going to guide us for how we find their areas. Now, the notes are going to be a little bit long. It's going to take some explaining to get through some of this stuff, so let's get started. Now, first definition, and this is an old one, but copy it down anyway. The term regular means that it is both equiangular and equilateral at the same time. Now, one of the things that we have not really discussed about regular polygons is that it has some other structures, some other little properties that are going on inside of those figures at the same time that all these angles and all these sides are ending up being congruent. Okay, so we're going to have some new vocabulary dealing with regular polygons. Now, the first one is a term that we have talked about in the past before, but you have never seen it as far as a non-circular shape is concerned, and the term is radius. Now, the term radius actually means the distance from the center point to a vertex is called the radius. Okay, now I'm sorry, that's what it's going to mean to our regular polygon. The distance from the center point of the polygon to a vertex is called the radius of the polygon. But more specifically, what radius actually means is furthest distance from the center, or furthest length from the center. Okay, now where a polygon is concerned, okay, that will mean from the center point out to vertex. Okay, in a circle, it did not matter where the radius was positioned because it's basically a tie. It was the same distance from the center point out to the circumference of the circle, no matter what direction we went. But in a polygon, that longest distance only happens when the radius reaches out and grabs a hold of a vertex. Okay, so here are several pictorial examples of where radii might be positioned. Now, obviously, those aren't the only vertices that the radii could position themselves at. Okay, in the quadrilateral on the left, there are 4 different places to put the radius or the radii. In the pentagon, there's 5 different places, and so on. Now, a term that you are most likely not familiar with also shows up in our regular polygons, and that term is apothem. Okay, and specifically what we're looking at here is the distance from the center point of the polygon directly over to one of the sides is what we call an apothem. Okay, so while the radius was reaching out to grab a hold of the corner points of the polygons, an apothem is reaching directly over to the side lengths. Now, apothem actually, the technical definition means shortest distance from the center point over to the side. And that shortest distance is going to occur by making a right angle with the connection to the side. Okay, so that's how come on all these 3 little diagrams we have there, you see I've got a right angle marked in there. That is where the shortest distance occurs, is when the apothem reaches directly over to the side and forms a right angle. And once again, there are other places that the apothem could be positioned in these diagrams. Okay, quadrilateral is going to have 4 different places for it. Pentagon's going to have 5. Hexagon's going to have 6, and so on. Now, let's take a look at why we're going to need these new terms and these new line segments in our figures. Okay. Let's take a look at the formula, and then you'll see where the significance of the apothem and the radius comes from. The area of the regular polygon is found by a formula, and that formula is 1/2 times A times P. 1/2 times A times P. Now I bet you can probably guess that A represents the apothem. Okay, that's the new guy that we've been talking about that reaches directly over to the side of the polygon. But we also have P. That's not anything we've talked about yet, but typically a lowercase p, when it shows up in a problem, is a perimeter of the polygon. Okay, now, so clearly you can see where the apothem comes into play, okay, where it's needed in the formula. But if you're a little curious about where the radius was important, well, let's take a look at this. Okay, if you take the information about an apothem and a radius in a regular polygon at the same time, look what happens. Apothem and the radius. You can see that between the apothem and the radius and the side of the polygon, right triangles are formed. And of course, anywhere there's right triangles, we have things like SOHCAHTOA, and we have things like Pythagorean theorem. Okay, but there you see it. Okay, the apothem and the radii, they generate a right triangle with half of a side length as their third side of the right triangle. That fact is going to be kind of an invaluable tool at our disposal when it comes to finding the information that plugs into our area formula. Okay, now we're going to take a look at a couple of special types of polygons here next. Okay, I do not want you to copy down everything that I'm getting ready to say. Just kind of keep it tuned in, listen to what I'm talking about, and I will key you in as far as the important information that goes along with what's getting ready to happen. So let's take a look at a couple of special regular polygons. Okay, so special regular polygons. One of them that we need to look at is the regular hexagon. Please write that down, a little subtitle in your notes, regular hexagon. Okay, now just kind of just follow along with me as I go here, and again, I'll let you know what to write down. Okay, here is a sketch of a regular hexagon. Okay, now if we were to take the diameters of the regular hexagon and draw them in, there would be 6 of them. And as you can see, the hexagon is divided basically into 6, slices of pizza, or however you want to think about it there, by those 3 diameters. Okay. Now, if we take that into consideration with the property of a circle. Okay, 1 revolution around a circle is 360 degrees. However, that property applies if you revolve in a circular manner, no matter if it's a circle or a hexagon or a decagon or any kind of shape. Okay, so if we take that 360 degrees and we separate it, divide it up equally amongst the 6 angles that are at the center of the circle, then what we find out is that all of the angles are congruent in there. So I've got 6 little angle congruency marks in there showing that all of those angles are congruent. Okay. Now, another property of the hexagon is, of course, since all of the diameters are congruent going through the figure, all of the radii are congruent as well. Okay, so I have marked all of them congruent by giving them all 1 tick mark each. Now, if we take this even further, okay, and consider the angles across from those side links in those triangles. Okay, did you notice in the figure that we ended up with little triangles, 6 little triangles, and we learned that if you have 2 sides of a triangle congruent, that means the angles across from those side links must also be congruent. Now, if you get to thinking about it, since we knew that the angles near the vertex, okay, or the center point of the hexagon, we knew all those were congruent, that would make all of those angles 60 degrees each. Okay, in each of these 6 triangles, Okay, we also know that the three angles in a triangle have to add to 180 degrees. So that means 60 degrees is already used up by the angle near the center point. That leaves 120 degrees to be now shared equally by each of the angles out near the perimeter. Okay, so what we find is that all of those angles are 60 degrees. So you can see I've got them all marked with one angle congruency mark. Okay. Now, even further, those base angles in each triangle, they end up being the same measurement as I just said. So that means that the third side of the triangle must be congruent to the other two. Since all three angles are the same, that means all three side lengths must be the same. Okay, so what we are looking at in this particular instance is we have a regular hexagon that by drawing in its three diagonals, okay, or three diameters, pardon me, we have six regular triangles. Okay, you need to copy down this diagram as well as the final statement. Okay, so go ahead and press pause, get this diagram copied down, and then once you're ready to move on, press play. Okay, now as we said, that means our regular hexagon is built by six regular triangles. Okay, copy that down. And now what we're going to do is we are going to take an even closer look at one of these six triangles. Now it does not matter which one of the six triangles we take a look at because we have discovered that all six triangles are identical. Okay, but we're going to take one of those triangles and we are going to pencil in the apothem. Okay, so the peak of this triangle that I'm showing you now, that is where the center point of the hexagon used to be. And an apothem has been drawn in. Okay. Now notice that the angle near the center of the hexagon is subdivided into two pieces, and as it turns out, that angle is bisected. Okay, because an apothem is perpendicular to the base of the triangle. Okay, since it was an isosceles triangle that is drawn in perpendicular, that makes it an altitude. That also makes it an angle bisector and a median and all of that good stuff as well. Okay, so the angle near the center has been bisected. Please copy this diagram down and this one final statement here about our hexagon. Now, since the triangle is isosceles, the altitude is also an angle bisector. That is going to cause our triangle, instead of being 60, 60, 60 on its three angles, it is broken into two 30, 60, 90 triangles. And as you recall from back in the day, we did talk about 30, 60, 90 triangles, and they have their special little rules to go along with them. Press pause if you need more time. And now let's take a look at the second regular polygon that is of special interest. Okay, and this one will be the square. Again, copy this one down, the title here, that we have a square. There's not nearly as much information to go along with this one, but I'll tell you what to copy down and when to copy it down. Okay, so we're going to start off with the basics, our friend the square. And once again, something happens in a square when you start to draw his diameters in place. Okay, so we're going to start off with one diameter. Okay, now obviously all of the angles in a square are 90s. Okay, but when you draw in the diameter, please notice that the diameter has split two of the 90-degree angles. As it turns out, it has bisected those angles, and as such, we end up with two 45, 45, 90 triangles inside of our square. And again, recall, we have some special rules for 45, 45, 90 triangles, and we'll refresh those when we need them. Okay. Now, taking this one step further, what happens if we draw in the other diameter? Well, once again, Okay, the second diameter coming in there does split the 90-degree angles into two equal pieces. So now we are looking at four smaller 45, 45, 90s. But this time now the right angle is down at the intersection of the diagonals. Okay, copy this diagram as well as that statement and this one final statement. Actually, this property of subdividing the triangles inside of a square, this property of it splitting them into 45, 45, 90s will continue as long as you continue to draw in altitudes of the square of the triangles in the square. So I'm going to take this diagram, I'm going to draw on it here for a second. If we were to draw an altitude into this bottom triangle, which I did not draw in the correct spot, my board's a little miscalculated. Okay, if we draw in an altitude, then that triangle has been split into two more 45, 45, 90s. There, again, two more, two more, two more. So now it's 8. And if you continue this process over and over and over again, now you've got 16, 32. Okay, and you can see that this can very, very quickly get almost entirely out of hand. Okay, but the point is you can continue dividing and subdividing your square by this process, and you will simply end up with more and more and more and more 45, 45, 90s. That may be important because of the 45, 45, 90 rules. Okay, now let's get back to our regular notes going on here, and let's see if we can't work some examples out. Now, as you will see, sometimes the information is provided for you nicely and you don't really have to do a whole lot of work to get things done. Sometimes you are missing information and it just takes a little bit more effort to get the job done. Find the area of the following regular polygon. Okay, obviously we have a pentagon. Okay, and it does not matter what type of a regular polygon it is. It can be a square or a pentagon or a hexagon or decagon or anything like that. The fact of the matter is it's regular. If it's regular, we have a formula that goes along with it, and that formula is 1/2 times the apothem times the perimeter. Okay, so let's examine the problem and see if we have the information that's needed. Okay, the apothem, do we have from the center point of the polygon directly over to one of the sides? Absolutely we do. Okay, we have that 4 in there. We know that that's the shortest distance because of the right angle marker that's in there. Now the perimeter, do we have the perimeter? Oh, they didn't come out and hand us the perimeter, but did they give us enough information for us to find it ourselves? Yeah, we know that the figure is regular. We know that a side length is 6, and if it's regular, that means all of the side lengths are 6. So 5 side lengths, all of them being 6 units each. So plugging into the formula, here's what we have. 1/2 is part of the formula, so it's still there. The apothem is 4, so we plug it in, and the perimeter is 6 units on each side times 5 total side lengths. It's just a big pile of multiplication from right there. We've got 6 times 5 out there. That's 30 times 4 is 120, and half of 120 is 60. 60 square units. Now that's not so difficult. Okay, but let's take a look at a one that may not be so polite with us. Find the area of the following regular polygon. Well, it happens to be an octagon, but that's not important. The fact of the matter is it is regular. Okay, but since it is regular, we have a formula. The area is found by multiplying 1/2 times the apothem times the perimeter. Okay, so let's look at the diagram and see what information we have. Okay, the apothem. Oh, this time the apothem is not known. It is not marked in the picture. Okay, it's part of a right triangle that we can see in there with the radius and part or half of a side length, but the apothem is not there, but it is a right triangle. I bet we can find it. Perimeter, did they give us the perimeter? Okay, well, it's not marked. They didn't hand it to us in the problem, but we have enough information to find it. There are 8 side lengths, and each side length is 10. So plugging the information that we have into the formula, okay, the apothem is the issue. Okay. However, as we've already said, the apothem is part of a right triangle. It's one of the legs of that right triangle. We have a leg of 5, an apothem that is unknown, and a hypotenuse of 13. Now, this is actually one of the Pythagorean triples. Hopefully, you are starting to learn this one. Okay, we have 5 and another leg and 13. This is going to be a 5, 12, 13 Pythagorean triple. If you could not remember that, then work it out. 5 squared is 25. 13 squared is 169. If you subtract the 25 to the other side, that is 144. Take the square root to get the square off of the a, and we have an a of 12. There is your 5, 12, 13. Okay, now that's great. That's not the answer, but it does give us a vital piece of information for the figure. We were unable to finish the area calculation because we did not know the length of the apothem. Now we know it. Okay, so let's plug that information into the formula. Okay, just a big pile of multiplication. Let's see what we have here. 8 times 10 is 80. 12 of them would be 960, and half of 960 is 480. 480 square units. So it's very similar to the type of problems we've been working in recent days. They don't always give us the information that we need, so we have to stop, solve for the missing information, and then figure out what to do about it. Okay, so as you can see, it does bring a new challenge to the table, but it is not an impossible challenge. It's just a new formula, and we have to deal with those formulas as they come. Anyway, I appreciate you finding time to do your notes. I will see you in class.